Okay, hi everyone. Finally, lecture 18. So more shortest path stuff. So we're going to be, well, path stuff. So the first part we're going to be talking about more stuff about matrix multiplication related to path problems. So in particular, we're going to be doing counting stuff because I know everyone loved counting the three colorings of Nova Scotia. So we're going to be counting paths using matrix multiplication. And then Floyd-Warshall, and then we're going to be doing shortest paths in DAGs. Okay, so matrix multiplication. So let's choose some graph. Doesn't really matter. Let's make it small. Okay, how about this? This seems like a nice general kind of graph. 2, 3, 4. So we start out by drawing the adjacency matrix of this graph. Right? So 1 just goes to, from 1 you can go to 3. From 2 you can go to 1 and 4. From 3 you can go to 2. And from 4 you can go to 3 and 4. Sorry, this is a 1 and 4. Okay, so that's the adjacency matrix of this graph. Notice it has this cool self loop, which is an edge that goes from a vertex to itself. Okay, equivalent representations of this graph. So suppose I ask you, how many paths are there? Distinct paths. From 1 to 3 that take 8 steps, okay? Well, yeah, 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. That's 1, okay? So we just saw 1 goes to 3, 3 to 2, 2 to 4, 4 to 3, 3 to 2, 2 to 4, 4 to 4, 4 to 3. Okay. There are others. I mean, when I put that loop in here to occupy 1 step, I mean, I could have put that loop the first time we went around. So you could, I mean, in a case like this, you can just count them. But on a bigger graph, this gets really, really cumbersome. So let's see if there's a neat way to do this using matrix multiplication. So what does M, the adjacency matrix, represent? It represents now, in general, this is binary because it says either there's an edge from vertex U to vertex V in 1 step, or there isn't. It's possible that you can also have what's called multi-edges, which are 2 edges going from the same vertex to the same vertex. Okay, so this is a multi-edge. In which case you wouldn't write a 1 in the adjacency matrix, you'd write a 2. Okay, so what does M say? Well, the entry in the ith row and jth column of M, so Mij is the number of ways to go from vertex I to vertex j in exactly one step. Okay. So, great so far, but we didn't want one step. We wanted 8 steps. So what can we do? Well, we can say, okay, well, suppose that we know how to do it for 1 step. Well, how would you do it how would you count the number of ways in 2 steps? Okay, well, the number of ways to go from U to V in exactly 2 steps is sum over, let's say, W, so another vertex. Take the sum over W of the number of ways to go from U to W in 1 step times, okay, I'm going to put this in a big square bracket later, the number of ways to go from W, okay, in exactly 1 step, to V in exactly 1 step. And then I'm going to put this in a square bracket. Okay. So does this start to feel sort of like counting the 3 colorings, where I said, okay, so you had the number of ways to 3-color Nova Scotia is the number of ways to 3-color Cape Breton Island times the number of ways to 3-color the mainland. Okay? Because, well, this is pretty much the same thing. You think, okay, well, suppose I can get from U to W. There are 5 ways for me to do that. And then there are 3 ways for me to get to W, from W to V. Then there are 15 ways for me to get from in 1 step and in 1 step. Then there are 15 ways for me to go to W in 1 step and then to V in 1 step. Because for every option you have to go from U to W, then you can choose any of the 3 ways to go from W to V, okay? I think I'm pretty sure you know this by now, okay? So, okay, so, and this is the sum over W. So, what does this look like? How is this familiar to us? Well, so let's look and say, so let's say that actually just for a moment, we're going to put that this is M, I'm just going to write M0, okay? Because this is going to be, I'm going to write the power of 2 here, okay? So it's 1 edge. This is the number of ways to go from each vertex to each other vertex crossing 1 edge, which is 2 to the power of 0. Okay, so yeah, let's stick with that. Okay, so now suppose I want the number of ways to do this in exactly 2, crossing 2 edges. So I'm going to write M sub 1, because 2 is 2 to the power of 1. So what is this? Well, the number of ways to go from vertex 1 to vertex 1 is, well, what is it? It's the number of ways to go from vertex 1 to vertex 1, and then vertex 1 to vertex 1, which is 0. So this entry of this matrix is going to be 0 plus the number of ways to go from vertex 1 to vertex 2, which is 0, times the number of ways to go from vertex 2 to vertex 1. The number, which is 1, so it's still 0. Number of ways to go from vertex 1 to vertex 3, which is 1, times the number of ways to go from vertex 3 to vertex 1, which is 0. So 0, 0. And then actually it's the number of ways to go from vertex 1 to vertex 4 in one step, times the number of ways to go from vertex 4 to vertex 1 in one step, which is 0. So this is all 0. Okay, surprise, surprise. There is no way to go from vertex 1 to vertex 1 in exactly 2 steps. What about to go from vertex 1 to vertex 2? Well, this is the number of ways to go from vertex 1 to vertex 1, which is 0, and then from vertex 1 to vertex 2, which is 0. And then it's the number of ways to go from vertex plus the number of ways to go from vertex 1 to vertex 3. Actually, I forget what we're multiplying. Oh, right. So now we're doing the number of ways to go from 1 to 2. Okay. So number of ways to go from 1 to 1, and then 1 to 2, plus number of ways to go from 1 to 2, and then 2 to 2, and then 1 to 3, and 3 to 2. Okay? So that's more interesting because that's the number of ways to go from 1 to 3. So that's 0 plus 0. Plus 1 times the number of ways to go from 3 to 2, which is 1. And then plus the number of ways to go from 1 to 4, and the number of ways to go from 4 to 2, which is 0 times 0 in one step. So this is 1. The number of ways to go from vertex 1 to vertex 2 in exactly 2 steps, there's one way. Okay, so if we think about it, all these times when we're saying, okay, we're summing over W, that was, it's kind of painful to do that manually. But you're actually saying, okay, the number of ways to go from U, so let's say this is U. Let's say 2 is U. 2 represents U. And you want to count the number of ways that go to V, which is this column, but you want to do 2 steps. So you want to sum over W, which is all the ways to go from U to something and then something to V. Well, what if, we're 13 minutes in, so I'm going to keep going. What you want to do, this trick, is actually going to be okay, so now suppose we want to go from the number of ways to go from 2 to 3, 2 to 3, in exactly 2 steps. Well, it's the number of ways to go from 2 to 1, okay, which is 1, times the number of ways to go from 1 to 3, which is here, okay? Because it's the number of ways, the row is where you're coming from, and the column is where you're going. So it's the number of ways to go from row 2 to column 1, times the number of ways to go from row 1 to column 3. So you multiply this one by this one, and it gives you 1. And then plus the number of ways to go from 2 to 2, and the number of ways to go from 2 to 3, which is 0. So this is, so far we've got 1 plus 0 plus number of ways to go from 2 to 3 times the number of ways to go from 3 to 3, which is 0. Number of ways to go from 2 to 4, which is 1, times the number of ways to go from 4 to 3, which is 1. So the number of ways to go from 2 to 3 in exactly 2 steps, there are 2 of them. So from 2 to 3 is 2. Okay? Surprise, surprise, this is matrix multiplication, right? When you multiply a column by a row in the same matrix, then it's saying all the ways to go from I to W, from U to W, as W ranges over this, and then it's saying, okay, and the number of ways to go as W ranges over this, this ranges over the same values. Then it's just the number of ways to go from U to W times the number of ways to go from W to V, and then you sum over W. Okay? So nothing hard. Okay? So how do you count the number of ways to go from each vertex, from each U to each W, from each U to each V in 8 steps? Well, you take the matrix, which is M0, and then you multiply it by itself and get M1. And then you multiply it by, you square M1 and you get M2, and you square M2 and you get M3. And M3 is the number of ways to go between U and for in the ith row and the jth column. That entry is the number of ways to go from the ith vertex to the jth vertex using exactly 2 to the 3 steps, which is 8. Okay? So it requires 0 times 0, 1 times 1, 2 times 2, and that gives you 3. So it's 1, 2, 3 matrix multiplications, and that gives you, and that's enough if you just want to do 8. So in general, if you want to do a power of 2 to the power of k, it's going to take you k matrix multiplications. Well, k matrix squarings, actually. So now what if you don't want to know about a power of 2, then you work out you do the squarings for the largest power of 2 smaller than the number you're interested in, and then you multiply, you look at the ones in the binary representation, the number you're interested in, and you do the corresponding multiplications. Okay, because if, for example, you wanted to do 6, then the number of ways to get from U to V in exactly 6 steps is the number of ways to get from U to W in 4 steps times the number of ways to go from W to V in 2 steps. Okay. So this is another reason, this is continuing on with what I was saying last time about why people get excited about speedups in matrix multiplication, because it lets you do other things faster as well. So, this is 19. What should I don't think we want to do this example in depth. So, yeah, so you use the repeated squaring. Okay, I think that's more or less it. So there is a question on the assignment about this, which is basically this, but a bit more complicated, because it's asking about alternating red and blue, or blue and red. So you just have to change this a little bit. So okay, what else can I say about counting paths? I think that's enough about counting paths. So okay, we can end after 20 minutes. So I'll come back and do Floyd Warshall. Ciao.